Okay, so today what I would like to do is to go over some more complex Lewis dot structures. So I want to start first by going over polyatomics, where you have a charge, and then we're going to go over exceptions to the octet rule. So what we call expanded octets, so those kind of exceptions. So let's start with some polyatomics first. So this sheet should be on under classwork. So if you guys can pull this out, so if you need to pull this out, you could pause this for a minute and then pull this back up or start it back up. So I want to go down here and do sulfate. So sulfate has a charge of -2. So I want to show you with the NaSl method how you would take this into account. So when we're doing the NaSl, the needed is going to stay the same. So sulfur needs 8, and we have 4 oxygens, and each of those need 8. So we have 5 times 8, so that's going to give us 40. The available is going to change now. So sulfur has 6 available valence electrons. Each oxygen also has 6. And now we're going to take into account this charge. So this tells us we have 2 extra electrons. That means we have 2 extra electrons available for our structure. So this gives us 32 electrons total. So now the shared is going to be the same. So we take 40 minus 32. That gives us 8. And the lone will be the available minus the shared. So that would be 32 minus 8 gives us 24 electrons. So this tells us that if we look at the shared, if we divide that 8 by 2, that tells us we have 4 bonds in our structure. So since sulfur is first, we're going to put sulfur in the middle, and we're going to put 1 oxygen off of each bond. So I know that sulfur usually has only 2 bonds, but in this case, since we have these extra electrons, we have a situation where we can have more than 2 bonds. So we're going to add 6 more electrons to each oxygen, because if you notice right now, they all have only 2 electrons. Now, if we do this, we're going to notice we have 6 electrons around each oxygen. So 6 times 4 gives us 24. And that's the number of lone electrons we would expect for our structure. We notice here sulfur has 8. But like I said, it does have more than 2 bonds. But since we have these extra electrons, that can happen in this situation. And then we're going to put brackets around our whole structure and put the charge outside the brackets to show that that has an overall charge. Okay, and I want to also do ammonium here. So let's look at ammonium. Ammonium is also polyatomic. So here we have NH4+. So in this situation, again, the needed is going to be this doing that the same. So nitrogen needs 8. Each hydrogen needs 2 since it satisfies the duet rule. So we'll have 8 plus 4 times 2. That's going to give us 16. Available, remember nitrogen has 5 valence electrons, so 5. Each hydrogen has 1 valence electron, so we'll have 4 times 1. Since we have a positive 1 charge, we're going to subtract 1 from that, so that gives us 8. Now, if we had not done that, we would have gotten an odd number of available. When you're doing these, you should never get an odd number for any of these, for needed, available, shared, or lone. If you were to have an odd number, that would indicate you have a free radical, and we're not going to do any free radicals. So always be careful if you're getting odd numbers, probably because you have some calculation mistake. Now, shared is going to be just like before. We're going to do 16 minus 8. that gives us 8 electrons, and lone is going to be 8 minus 8. That means we have 0 lone pairs or lone electrons. So now, since nitrogen is written first, we're going to put nitrogen in the middle. We're going to make it symmetrical and put a hydrogen on each side. And then we're going to put one bond to each hydrogen. If we notice here, 8 divided by 2 is 4. That gives us 4 bonds. We're seeing 4 bonds. We have each hydrogen is happy. It doesn't need any more electrons, and the nitrogen has 8. So now we're going to put brackets just like before around this, put a positive 1 charge for the overall charge, and we're done. Okay, so now we're going to go over expanded octets. So I want you guys to look at sulfur hexafluoride. So when you run into situations where you see hexa or penta in the name of your compound, that tells you that you have an expanded octet. However, sometimes students forget this and they start doing the NaSL method and they get weird results. So I'm going to start it by doing that in case you forget to watch out for this. So first of all, sulfur hexafluoride is SF6. So if we do this, we would start out by writing your needed is 8 plus 6 times 8, and that gives you 56 electrons. Available would be 6 plus 7 times 6. That would give us 48 electrons. So if we do our shared, we're going to see we have 56 minus 48. That gives us 8 electrons, and that would tell us we only have 4 bonds. So hopefully at this point you would think, this doesn't seem right because I have 6 things bonded to sulfur, but I only have 4 bonds. That's impossible. So this is because we have an expanded octet. So if you're getting a strange number of bonds for your structure, that's probably what's happening. So we're going to put sulfur in the middle. So when you run into this, you're just going to put your first one in the middle, and you're going to put fluorines around either side of it with a bond. And then I'm actually going to erase this part here so I have more room. And what I'm going to do is I'm just going to put 6 more electrons around each fluorine to make sure each fluorine has enough electrons. Okay, so now what I want to do is I want to calculate how many electrons I'm using and compare that to my available. So I see here that each fluorine has 6 electrons around it. So that's 6 times 6 is 36. And then I see that I have 5 bonds. So 6 bonds. So I have 6 times 2, which is 12. So 36 plus 12 is 48, which is the number we have available from our valence electrons. I also want to make sure, if we look at our periodic table, sulfur is in the 3rd period. So this can happen anytime you have an element that's in the 3rd period or lower. So you might see this with sulfur, selenium, tellurium, or maybe chlorine, bromine, or iodine. So when you have one of those elements, you want to watch out because this could happen. And like I said, if you see hexa, then or a penta, then that's what's happening here. Okay, so guys, to practice this, I want you to pause the screencast and I want you to try this problem here. So I'm going to highlight the phosphorus pentachloride to just practice with an expanded octet. Once you've completed that, you can start the screencast again, and if you have any questions, just let me know. Okay, so let's go over phosphorus pentachloride. So with this one, make sure always when you have penta or hexa that you're still calculating the A, even though you're not doing the NaSl. So with our formula, we have PCl5. So our A would be 5 plus 5 times 7, which gives us 40 electrons. So we want to make sure as we draw a structure that we're using that many electrons. So we would put phosphorus in the center, and we know that phosphorus is in the third period, so we're allowed to do this with phosphorus. And then we have 5 chlorines around phosphorus. So hopefully you drew this. And then you want to make sure each chlorine has 8 electrons around it. It still wants 8. So hopefully you had this next. And then what we want to do is we want to count how many electrons we're using and make sure we're using 40. So I see that I have 6 electrons, lone electrons around each chlorine. So 6 times 5 is 30. And then we have 10 electrons here. So 30 plus 10 is 40, which is what we have available. Okay, so now what I want to do is I want to go over another type of expanded octet, which you will not, it will not be as obvious because you won't see like hexa or penta with the name. So let's go over chlorine trifluoride. So for chlorine trifluoride, if you were to start doing the NaSl method for this, you would start getting some very strange answers. So let's do the needed. So first of all, chlorine trifluoride is ClF3. So the needed would be 8 plus 3 times 8. And that would give us 32. The available would be 7 plus 3 times 7. That would give us 28. And then the shared would be the needed minus available, so 32 minus 28. That would give us 4. And if we look at it, this is telling us that we only have 2 bonds in our structure. But if we look at this, we have chlorine bonded to 3 things, and that's telling us that we should have at least 3 bonds. Now, the reason why we're getting strange results like this is because we have a situation where we have an expanded octet. Now, the available is still very important. So when you're doing the NaSl and you don't end up needing to do the NaSl, you need at least to look at the available, the number of valence electrons. So we're going to put chlorine in the middle since it's first in our structure. And we're going to put 3 fluorines around this with a bond to each fluorine. Now what we're going to do is make sure each fluorine has 8 valence electrons. So we're going to add 6 more electrons to each fluorine. We're then going to make sure that chlorine also has 8. Now, if we start counting up our electrons, we want to make sure we're using 28 electrons in our structure. So we see here we're using 6, 12, 18, 20, 22, 24, 26. We're only using 26 electrons in our structure, yet our availables tell us that we should be using 28. So in a situation like this, we're going to add more electrons to our central atom because that is expanding the octet. Chlorine is in the third period. It's able to expand its octet. Fluorine is only in the second period. It cannot expand its octet. So we're expanding chlorine's octet. So there's 2 different ways you can write this. Sometimes you will see people draw a line to the central atom, just indicating that this last pair of electrons is attached to the central atom only. That line does not mean that there's electrons attaching those electrons. So that if we count this up, we have 6, 12, 18, 20, 22, 24, 26, 28 electrons. Sometimes instead this is drawn, let me show you here, as 2 pairs on that central atom. So you could draw either way. And again, this is using 28, which is what we have available. So that is an expanded octet. And I want you guys to try Xenon Difluoride, so pause the screencast and try that. Okay, so let's try Xenon Difluoride. So hopefully you had some idea what to do. We'll just go over the answer here so you guys can see if you're doing this the right way. Again, always make sure you start out by calculating your available. So we have Xenon Difluoride is this. So we see our available is 8 plus 2 times 7. So that gives us 22 electrons available. So when we do this, again, we put these first one in the middle, xenons in the middle, and we put 2 fluorines on either side. And we first make sure we have 8 electrons around each. Okay, when we do this, we calculate how many we're using. We see we're using 6 plus 6 is 12, 14, 16, 18, 20, but we're supposed to be using 22. So in this case, we're also going to be adding 2 more electrons to our central atom. If you look at xenon, it's on the 5th period on our periodic table. So that tells us that xenon is allowed to expand its octet. Now, we can draw a line like we did with chlorine trifluoride originally and put 2 more electrons to show that these 2 electrons are attached to xenon. Again, this line does not mean that there's 2 electrons attaching those 2 electrons. We're using 6, 12, 14, 16, 18, 20, 22, which is what we have available. Or we can draw those two other pairs like this around xenon. So either way is acceptable. Okay, so work on this worksheet. If you have any questions, please let me know. Before you work on it, though, I'm going to point out a few things. So first one is, if you look at ethene, ethenes should be C2H2. Ethane is C2H6. When you get to oxygen gas, remember that's diatomic, that'll be O2. And nitrogen gas is also diatomic, that will be N2. And methane is CH4. And ammonia is NH3. And ozone is O3. Okay, so everything else you should be able to do, and good luck.